So this is a little video to try and give you some strategies for the find the rule questions that always turn up in the on-screen exam at the end of NYP5. Now we're going to talk about three different kinds of rule that tend to appear in this video. And the first kind is a linear rule. So the n's here are just the position in the sequence. So when n is 1, we're talking about the first term, the second term, the third term, the fourth term. So it's just the marker that labels where you are in the sequence. And then the sequence itself, it's called P. So P equals 5, 8, 11, 14. The first term of P is 5, the second term of P is 8. And you notice very quickly, if you're observant, that they go by up by 3 every time. From 8 to 11 up 3, from 11 to 14 up 3. So what you're often asked to do in an exam question is to continue the sequence. And if you can see the pattern, without even being able to figure out an algebraic rule for it, it's quite easy to continue that as 17, 20, 23, 26, and so on. Now, when you've got a linear rule like this, and they're just going up by a certain amount every time, that certain amount gives you a big clue as to what the rule is, because every time the n's are going up just by 1, it's making the p's go up by 3. So that's giving you the clue that working out the p's involves somewhere multiplying the n's by 3. So think about if the rule was just 3 times n, then the numbers we get would be 3 times 1 is 3, 3 times 2 is 6, 3 times 3 is 9, 3 times 4 is 12, 3 times 5 is 15, and so on, 18, 21, 24. So we do get some numbers that go up by 3 every time, but they're not the ones we want, because the ones we want are not 3, 6, 9, they are 5, 8, 11. So we've got to think about what do we need to do with these in order to get these. And it's quite easy to see that you just have to add 2 to all of them. So if you make the rule 3n plus 2, then you do indeed get the numbers that you want matching the sequence. So that means that our rule is that p equals 3n plus 2. And now that you've got a rule like that, you could use it to figure out like the 1000th term just by sticking in 1000 there for n and getting 3002, and you wouldn't have to work out the previous 999 terms in order to do that. Okay, so here's another example of a linear rule. Pause the video for a bit and just try and have a go at this yourself. So fill in the next missing few terms, figure out the rule, and then these boxes are just for working that I'm going to do, and then say what the rule is at the end. Okay, so I'm just going to allow you to pause the video, and I'm revealing the answers in 5, 4, 3, 2, 1. Here we go. Okay, so the terms are going down by 4 every time, from 2 to minus 2, down to minus 6, down to minus 10. So it's minus 4 every time. So it's easy to continue subtracting 4 to get the next few terms. There they are. So the fact that it's got a minus 4 tells us that the rule must have something to do with minus 4 times n. But if the rule is just minus 4 times n, then the numbers we get are these ones, minus 4, minus 8, minus 12, minus 16. So these go down by 4 every time, but they're not the ones we want, because we want 2, minus 6, minus 10. So we need to ask ourselves the question, what do I need to do to all of these numbers in order to get up to these numbers? And the answer is I need to add 6 to all of them. So the rule minus 4n plus 6 does give you the numbers that you're aiming for. And so the rule is minus 4n plus 6. Q, I've called it Q this time, equals minus 4n plus 6. Okay, so that's all in this video for linear sequences. I'm now going to talk about geometric sequences. Now in a geometric sequences, you're not adding the same amount every time, these go up by bigger amounts every time. But what is happening here is that each term is bigger than the other one by a factor of a certain number. So 2, in this case, times 3 is 6. 6 times 3 gives you 18. 18 times 3 gives you 54. Now it's easy to figure out what that factor is just by working the thing backwards. So if you do 6 divided by 2, then you get the 3. So you figure out how many times bigger the next one is than the previous one. And in this kind of sequence, as you can see, each term is always 3 times the previous one. So generally, this is a geometric sequence, and in a geometric sequence, each term is a fixed amount times bigger, or times as big as, the previous one. So once you've figured out that it's times 3 every time, it's easy to continue multiplying by 3 to get the next few terms. That's straightforward. But what about turning that into a rule? So let's just think of these numbers as being, well, so they're called R. I've called them R this time. The first one is 2. The next one is 2 times 3. And the next one after that is the previous one times another 3. So it's 2 times 3 squared. And then each one is bigger by multiplying it by 3 again. So the next one is 2 times 3 cubed. The next one is 2 times 3 to the power of 4. And when you write them like this, they all kind of look the same. They're all 2 times 3 to the power of something, except that power of something is increasing by 1 every time, very much in the same way as the n numbers are increasing by 1 every time, except that the numbers here are 1 less than the n numbers. So that means that the rule must be 2 times 3 to the power of n minus 1, or in other words, 2 times 3 to the power of 1 less than the n numbers. Okay, so I've called these R, so it's R equals 2 times 3 to the power of n minus 1. Here's another geometric sequence. It's a little bit different, you'll figure out why. Have a go at it, pause the screen, and I will go through the answer shortly. Okay, so I'm going to reveal the answer in 5, 4, 3, 2, and 1. This time, the terms are getting smaller, but you can still get from each one to the next one by multiplying by something. You just multiply by a fraction. So 64 is a half of 128, I hope you noticed. So you can say 128 times a half gives you 64. 64 times a half gives you 32, and each time it's times a half. So as you can see, I've continued the sequence. 16 times a half is 8, 8 times a half is 4, 4 times a half is 2, 2 times a half is 1, and you could carry that on. So let's think about writing these numbers in a different way. So the first one is 128, the second one is 128 times a half, or 128 times 0.5, that's the same thing. The next one is times another half, so it's 128 times a half squared, and the next one is 128 times a half cubed, because it's the previous one, but times another half. So once you write them all like this, they all kind of look the same. They're all 128 times 0.5 to the power of something, except that something is always 1 less than the n number. So the rule is that S, in this case I've called it, equals 128 times 0.5 to the power of n minus 1, 1 less than n. Oh, by the way, for all of these, the first term looks kind of different, but it's still working because, according to the rule, the first term would be 128 times 0.5 to the power of 0. And of course, anything to the power of 0 is just 1, so that would still give you 128 as the answer. So even though the first one's written in a different way, the answer that the rule gives is consistent. Okay, now there is a third type to watch out for that does come up from time to time. So if you look at these ones, they're not increasing by a fixed amount every time because it's going +4, +6, +8. You're not multiplying by the same thing every time because from 2 to 6 is times 3, but from 6 to 12 is only times 2. But there is a pattern to this. Now if we think about the differences between these terms, they go +4, 2 to 6 +4, 6 to 12 +6, and they're going +4, +6, +8, +10, +12, +14, +16. And there certainly appears to be a pattern to that. And if we think about the differences between the differences, so from 4 to 6 is +2, from 6 to 8 is +2, and then these, well, they're called the second differences for obvious reasons, and the second differences are the same every time. When the second differences are the same every time, that means the rule is a quadratic. Now you remember quadratic from the beginning of MYP4 as being to do with powers of something up to squared. So the rule is going to be something like t equals something with n squared in it. So let's think of the simplest thing we could have. If the rule was just n squared, then we get 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64. Now these aren't the numbers we want, because the numbers we want are 2, 6, 12, 20, 30, 42, 56, 70. Let's just think about the differences between the numbers we've got from this rule. So they're going +3, +5, +7, +9, +11, +13, +15. And the second differences of those are still 2 every time, like before. So that suggests that we've got the n squared bit right. We just need to do something with the lower powers of n's, like n on its own or a constant number. So let's think about the numbers we're missing now. So we got a 1 from this rule, but we're aiming for a 2, so we are missing 1. We got a 4 from this rule when we wanted a 6, so we're missing a 2. We got a 9 from this rule when we wanted a 12, so we're missing 3. And you can see the numbers that we're missing are going 1, 2, 3, 4, 5, 6, 7, 8, and so on. And those are just the n numbers. So if we try n squared, but then add the n numbers and get n squared plus n, then we get 1 plus 1 is 2, 4 plus 2 is 6, 9 plus 3 is 12, and we're getting the right numbers. We're getting the ones we want: 2, 6, 12, 20, 30, 42, 56, 72. So in this case, the rule is that t equals n squared plus n.